Good evening, GCC. So next part right here, this is kind of a key lesson in this chapter, 6.6. Logarithmic and exponential functions. Here's where we're going to see them side by side, working together, inverses of each other, and all those properties. So this is the kind of the bringing everything together that we've done in 6.1 through 6.5, all the concepts, all the properties, all of these things, and working how they work together and solving equations. The equations that we do here are just going to be regular, everyday equations, nothing too fancy going on. And then the rest of the chapter, 6, 7, 8, and 9, are all the applications, the financial and all the other things that we can do with exponentials and logarithms. So this is really kind of a key lesson in this chapter. In many ways, for today's lesson, there's nothing new. There's no new we've done all the properties. There's no new properties. There's no new types of anything going on. It's just bringing them all together and solving them. So really, my lesson for tonight is going to be a lot of sample problems. Make sure you're taking good notes. If you need to pause the videos to get these stuff written down, then do it. We need to remember that y equals log base a of x is equivalent to, if I rewrite this, it would be a to the power of y equals x. That's probably one of the most important properties, rewriting it between the logarithmic form and exponential form, or exponential form and logarithmic form, rewriting these. All right, so as I said, my whole lesson for tonight is just a bunch of sample problems as we go through these things. So here we go. So example number 1. I want to solve log base 2 of 1 minus 2x is equal to 3. Now, as we can see here, I think we can see that one of the keys to doing this is to rewrite it. So the first thing I'm going to do is rewrite that. And when I rewrite it, I'm going to get 2 to the power of 3 equals 1 minus 2x. This I can solve a lot easier. 2 to the power of 3. 2 times 2 times 2 is 8 equals 1 minus 2x. Subtract 1 from both sides. 7 equals negative 2x. Divide both sides by negative 2. And x equals negative 7 halves. And there's my solution. So a lot of these, when you know what you're doing, they're pretty quick and they're pretty straightforward, but they're using all these properties that can be very confusing and very frustrating. All right, so let's do a bunch more examples here. Really, my whole lesson tonight is 45 minutes worth of example problems. Normally in class, I would also be doing, asking questions. Did we get this? Did you understand that? And then I would be picking and choosing other examples based on the feedback that I was getting in class. All right, so here we go. Example number 2. And I want to solve 2 times the log base 5 of x equals log base 5 of 9. Now, rewriting is going to be one of the keys here, but before I do, or maybe rewriting is, I'm not sure. I've got them both on sides. I'm going to deal with this power here. I'm going to put the 2 up there. I'm going to use power rule. And I get this. Log base 5 of x squared equals log base 5 of 9. Now, take a closer look at this. Do I need to rewrite this? Look at what it's saying. Log base 5 of this equals log base 5 of that. Well, if the log base 5 of this equals log base 5 of that, doesn't it make sense that this and that have to equal each other? In other words, x squared has to equal 9. Take the square root of both sides, and I get x equals plus or minus 3. I'm getting 2 solutions here. X could equal 3, and x could equal negative 3, because 3 squared is 9, negative 3 squared is 9. But wait a minute. I think I've got two solutions, but when I look back in my original problem, where is the x? It's in the argument, log base 5 of x. And can I take the log of a negative number? No, it's not part of its domain. That negative 3 is an extraneous solution. Does not count, is not part of the solution set. So really, I'm only getting one solution here. All right, let's take a look at another example, example number 3. And example number 3, I want to solve log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. And I want to solve this. Oh, a lot more going on in this one. The first thing that occurs to me is that I can combine these two logarithms. Product rule. If I combine them, I'm going to get log base 5 of x plus 6 times x plus 2 equals 1. I'm going to simplify the argument here. Remember, product means adding them. I'm going to FOIL these out, and I get log base 5 of x squared plus 2x's plus 6x's plus 12 equals 1. Now what? Well, let's see. Now I think this is where I would rewrite. Notice I've got a nice basic equation here. Log base 5 of this equals that. So 5 to the first power equals this. 5 to the first power equals x squared plus 8x plus 12. Simplifying this, 5 to the first power is 5. Subtract 5 from both sides, and I get a nice, well-behaved quadratic. Let's see, 12 minus 5 is 7. So it kind of, this problem, which started as this big, horrible, nasty, ugly logarithmic equation, has boiled down to a nice, well-behaved quadratic. And what's more than that, this is, I don't need anything too fancy-schmancy here. I can actually solve this one by factoring. It's going to factor nicely. Two things that multiply together to give me 7, add up to give me 8. How about x plus 7, x plus 1? Set each factor equal to 0. X plus 7 equals 0. X has to equal negative 7. X plus 1 equals 0. X has to equal negative 1. So I'm getting two solutions. But as we saw before, we really want to check these solutions. Am I allowed to have these solutions? I know I can't take the log of a negative number, but I want to look back in my original equation. So I'm going to take these solutions, and I'm looking back in my original, this blue equation up here. Can I plug negative 7 in? If I plug negative 7 in here, negative 7 plus 6, I get negative 1 here and negative 5 there. Can't take the log of a negative number. That answer is no good. Maybe neither one of these are good. Maybe there's no solutions here. Well, can I plug in negative 1? If I plug negative 1 in here, I get 5, and I get 1 there. So even though x is negative, when I plug it in, I'm not getting negative logs, so that answer is actually good. That one works. Another one. Example number 4. For example number 4, I'm going to have, I want to solve, and let's talk about natural logs this time. The natural log of x plus the natural log of x minus 4 equals the natural log of x plus 6. All right, let's see what I want to do here. It occurs to me that I can combine these two using properties of the logarithm, and I get the natural log of x times x minus 4 equals the natural log of x plus 6. And then if I simplify this out here, I get the natural log of x squared minus 4x equals the natural log of x plus 6. Now look at what I've got. The natural log of this equals the natural log of that. If the natural log of this equals the natural log of that, then doesn't this have to equal that? X squared minus 4x equals x plus 6. subtract x from both sides, subtract 6 from both sides, and again, this very difficult, confusing logarithmic equation kind of boils down to a nice, well-behaved quadratic. And what's more than that, this is nice and easily factorable. If it wasn't factorable, what would we have to do? Well, we'd have to use either completing the square to solve it or a quadratic formula. But this one, I can think of two things that multiply together to give me negative 6 and add up to give me negative 5. Negative 6 and positive 1. Set each factor equal to 0 and solve. And I get x minus 6 equals 0, so x could equal 6. X plus 1 equals 0. X could equal negative 1. But I need to check these solutions. Am I allowed to have these solutions? If I plug 6 back in here, I get a positive argument. 6 minus 4 is positive. 6 plus 6 positive. Okay, I'm allowed to have 6. None of my logarithms become negative. How about negative 1? The natural log of negative, oh, that one becomes negative. So nope, can't have that solution. That's an extraneous solution there. So the only answer is going to be the 6. All right, let's keep going here. Example number 5. I want to solve 2 to the power of x equals 5. So this is an exponential equation. 2 to some power equals 5. Well, I know that, let's see, 2 squared is 4. 2 squared is 4, and 2 cubed is 8. So x has to be somewhere between 2 and 3, because 5 is somewhere between 4 and 8. But how am I going to find it? It's not going to be a nice number, is it? It's going to be some sort of weird number. How am I going to solve this? All right, I'm going to start by take the natural log of both sides. I'm not multiplying by the natural log. I'm taking the natural log of 2 to the x, and I'm taking the natural log of 5. This helps because I can use properties of logarithms. Power property. I'm going to bring the x out in front. X times the natural log of 2 equals the natural log of 5. Natural log of 2 is just some number. I'm going to do it on the calculator in a minute. Natural log of 5 is just some number. Divide both sides, and I get x equals the natural log of 5 over the natural log of 2. Grab the calculator. And natural log of 5 divided by the natural log of 2. And I get 2.3219. Between 2 and 3, just like we thought. Now be careful, because this, it's not the same as the natural log of 5 over 2. That's something completely different. The natural log of 5 divided by 2 is 0.916. So be careful when you're doing this. This is the natural log of 5 divided by the natural log of 2, not the natural log of 5 divided by 2. Are you seeing that difference there? Are you seeing that very important? All right, let's take a look at another one. Example number 6. And example number 6, I want to solve. A little bit more difficult now. 8 times 3 to the x equals 5. I say a little bit more difficult because this one I'm looking at it and I have no idea at all. And the other one we just did, we could guess. We knew the answer was going to be between two numbers here. I'm going to get rid of the 8, divide both sides by 8, and I get 3 to the x equals 5/8. Well, let's see. 3 to the first is 3. 3 squared is 9. 3 cubed is 27. 5/8, though, that's less than 1. Well, 3 to the 0 power is 1, so x is going to be less than 0. 3 to the 0 power is 1. This is less than 1, so x is going to be some number less than 0, but what on earth is it? Well, even though it's going to be a little bit more difficult, we're going to end up with a negative answer here. I'm going to do it exactly the same way as we did the last one. We are going to take the natural log of both sides. And when I do, I'm going to have the natural log of 3 to the x equals the natural log of 5/8. Use properties of logarithm. x times the natural log of 3 equals the natural log of 5/8. This is the natural log of a quotient. I could rewrite it as the natural log of 5 minus the natural log of 8, but I don't want to do that. This is just going to be some number here. Natural log of 3 is just some number. Divide, and I get the natural log of 5/8 divided by the natural log of 3. Oh gosh, be careful how you do this on the calculator. Let's take a closer look at the syntax on the calculator here. So I'm going to have the natural log of 5 divided by 8, close parentheses, divided by the natural log of 3, close parentheses, is, now remember we said we think it's going to be a little less than 0, and sure enough, there it is, negative 0.4278-ish. So again, a little bit more awkward, a little bit more going on in this one. Let's continue, do some more examples. Example number 7. Example number 7, I want to solve 5 to the power of x minus 2 equals 3 to the power of 3x plus 2. Now, we saw one similar to this earlier on in the chapter, but I could rewrite both of them with the same base. I think we dealt one in class where it was an 8 and a 4, and I rewrote them both with bases of 2s. 5 and 3s. I cannot rewrite them with the same base. That is not going to work here. This one is going to be very difficult to do algebraically. What I need is I need to get the variables out of the exponent. How do I do that? Properties of logarithm. So I'm going to take the natural log of both sides. Now, be careful with this one. Follow very carefully with this one. And as I do, I'm going to get the natural log of 5 to the x minus 2 equals the natural log of 3 to the 3x plus 2. I'm going to use properties of logarithms. And this x minus 2, I'm going to bring it over here. X minus 2 times the natural log of 5. This 3x plus 2, I'm going to bring it out in front, multiply 3x plus 2 times the natural log of 3. I want you to focus on the fact that the natural log of 5 is just some number. The natural log of 3 is just some number. Okay, so I'm going to distribute the natural log of 5 in here. And I get the x times the natural log of 5 minus 2 times the natural log of 5 equals 3x times the natural log of 3 plus 2 times the natural log of 3. And I distributed the natural log of 5 and the natural log of 3. Remember, the natural log of 5 is just some number. This is a number with a variable. This is just a number. This is a number with a variable. This is just a number. I'm going to get this term. I'm going to subtract this term from both sides. And I'm going to get x times the natural log of 5 minus 3x times the natural log of 3. That should be a 3, shouldn't it? I've still got that term over there too. Minus 2 times the natural log of 5 equals 2 times the natural log of 3. This is just some number. I'm going to add it to both sides. Now I'm going to have x times the natural log of 5 minus 3x times the natural log of 3 equals 2 times the natural log of 3 plus 2 times the natural log of 5. Oh, excuse me. Now what I'm doing is I'm gathering all the terms that have got x's on one side and all the terms that don't have any x's in on the other side. This is just some number. That's just some number. On this side over here, I'm going to factor out the x. If I factor out the x, here it is out front, what do I have left? Natural log of 5 minus 3 times the natural log of 3 equals, over here I have 2 times the natural log of 3 plus 2 times the natural log of 5. I factored out the x. The x is the only variable. Everything else is a number. Divide both sides by this number, and I get a very complicated x equals 2 times the natural log of 3 plus 2 times the natural log of 5 all over the natural log of 5 minus 3 times the natural log of 3. And this is just some number. I'm going to have to evaluate this on the calculator. It's going to be tough. There's a lot of stuff going on in here. I have to be very careful. Parentheses. So I'm going to put this whole thing in parentheses up here, the whole thing in parentheses down there. So I'm going to open parentheses, 2 times the natural log of 3, close parentheses, plus 2 times the natural log of 5, close parentheses. That gives me the whole numerator, divided by, open parentheses, natural log of 5 minus 3 times the natural log of 3, close parentheses. And I get x equals negative 3.2116 approximately. Oh gosh, some horrible answer there. And I had no idea going into this one. This was one of the ones where at no point could I look at it and say, oh, I think it's going to be about this, or I think it's going to be about that much. No, very, very difficult problem. All of these problems that we're solving algebraically, they can be done on the calculator as well. And we'll take a look at solving them on a calculator. Right now I want to emphasize solving them algebraically using all the properties. And then later we'll definitely look at solving them on the calculator. All right, so the next one, let's see, example number, what am I up to here? 6 or 7? Example number 7, am I up to 7? Let's see, solve 4 to the power of x minus 2 to the power of x minus 12 equals 0. All right, so another tough one. Gosh, where would we even start something like this? Well, I'm going to rewrite the 4 as 2 squared. That's my 4 to the x minus 2 to the x minus 12 equals 0. So all I did was I rewrote 4 as 2 squared. I'm going to simplify this expression. Power to a power we multiply. This is 2 to the 2x minus 2 to the x minus 12 equals 0. I could rewrite this. This was 2 to the 2 to the x. I'm going to rewrite it as 2 to the x squared minus 2 to the x minus 12 equals 0. See, here I had 2 to the x, which is 2x, which is the same thing as x to the 2. Okay, x to the 2 and 2x and 2 to the x, they're all the same thing. Why am I looking at this? Because now I've actually got it in quadratic form. I've got something, I'm going to put a great big U here, squared, and the same something here. So I've got something squared minus something minus 12 equals 0. If you want to rewrite it to make it look a little nicer, I could say u squared minus u minus 12 equals 0, where u is really just 2 to the x. I'm rewriting it to make it look a little nicer and to show you that this is a quadratic. This is a nice, well-behaved quadratic, and it's factorable. Can I think of two things that multiply together to give me 12 and add up to give me a negative 1? And of course the answer is yes. I can factor this to u minus 4, u plus 3, right? Negative 4 times 3 is negative 12. Negative 4 plus 3 is negative 1. This factors. But wait a minute. I don't really have u's here. I just put the u's in there so that we can kind of see the quadratic a little clearly. Really, it should be 2 to the x's. The u really should be 2 to the x. This really should be 2 to the x minus 4, 2 to the x plus 3. Now that it's factored, set each factor equal to 0. 2 to the x minus 4 equals 0. 2 to the x plus 3 equals 0. Solve. 2 to the x equals 4. 2 to what power is 4? 4 is 2 squared. Oops, that should be an x. Therefore, I get my first solution here. X is 2. There's one solution. What about looking at the other solution here? Here I get 2 to the x equals negative 3. And as I take a look at 2 to the x equals negative 3, 2 to the x, am I ever going to get a negative number? Think about the graph of 2 to the x. No matter what you plug in for x, you'll never get a negative number. It's not part of its range, domain rather, or range. Domain is all real numbers, but it never becomes negative. There's no solutions there. So the only answer is 2. So the original equation here, 4 to the x minus 2 to the x minus 12. 4 squared is 16, minus 4 squared is 4. 16 minus 4 is 12. 12 minus 12 is 0. So yeah, it does work. It checks out. That does work. All right. Now what I'd like to do is I want to talk about some of the problems from the homework and do some sample problems from the homework. The homework is on page 472, and I've got a couple of different sets here. Basically, it's all solving. Problems 5 through 27 odd, a lot of rewriting and solving. Problems 33 through 41 odd, 45 through 49 odd, and then some 161s and some later ones. And what I'd like to do is just a couple of sample problems out of the exercise set. So the first one I'd like to do is problem number 20. And 20 is a solving. The log of 2x minus the log of x minus 3 is equal to 1. And I want to solve this. All right. First thing that occurs to me is I can combine these. Quotient rule becomes the log of 2x over x minus 3 equals 1. So the first thing I did was properties of logarithm, combine them. There were no powers out front that I had to deal with. Now I'm going to rewrite. So log, what's the base here? This is common log, so the base would be 10. So if I rewrite it, 10 to the first power equals that. 10 to the first power equals 2x over x minus 3. And of course 10 to the first power is 10. If I cross multiply here, 10 times x minus 3 equals 1 times 2x. Distribute, 10x minus 30 equals 2x. The more we simplify, the easier this thing becomes. We started with a very difficult logarithmic equation here. After rewriting it, we got what seemed a difficult equation to solve, and it's getting simpler and simpler here. Subtract 10x's from both sides. Negative 30 equals negative 8x. Divide by negative 8, and x is negative 30 over negative 8, which I can simplify to 30. I don't want to use another piece of paper just for 1 or 2 lines. 30 over 8, 15 over 4. If I simplify negative 30 over negative 8, I get 15 over 4. All right, let's do another problem out of the exercise set. Let's see. And this is where I would kind of talk, and I would ask you, and I'd kind of get a feel, ask you to look at them, see if there's any questions, and then I would try to pick one that's very similar to it. So I want to pick something a little different than what we just did. Let's see. How about, well, 32 is a kind of a weird one. Let's take a look at number 32. It says log base a of x plus log base a of x minus 2 is equal to log base a of x plus 4. And one of the things that makes this one kind of weird is that whole base a thing going on there. Well, I don't know what the base is. Can I really solve this if I don't know what the base is? And the answer is yes. I notice that I can combine these two logs here, and I would get log base a of x times x minus 2 equals log base a of x plus 4. Multiply this out. Log base a of x squared minus 2x equals log base a of x plus 4, 8. Why is that an 8? That should be an a. a. And here's where we can see that the base doesn't really matter, because I've got log base a of this equals log base a of that. Therefore, this must equal that. And again, I get that nice well-behaved quadratic. Subtract x's from both sides. Subtract 4 from both sides. And this whole thing, this very difficult, weird logarithmic equation with base a's, and I was wondering, oh, how are we going to deal with that, has all boiled down to a nice, well-behaved quadratic. And it's factorable. Can I think of two things that multiply together to give me -4, add up to give me -3? How about -4 and 1? Set each factor equal to 0. It seems like I'm always running out of space here. You have to use at least one more page just for a couple of lines. X minus 4 equals 0, therefore x equals 4. X plus 1 equals 0, therefore x equals -1. I want to check these solutions. I want to take these two solutions and I want to plug them in, and really what I'm looking for is, will the arguments be negative? If I plug in 4, that's going to be positive, positive, positive. Then the 4, that's okay. If I plug in -1, oh, right there, it's going to be negative. If I plug in -1, that one is not okay. That's an extraneous solution. Can't have it. All right, let's take a look at another one. How about number 42? This one says 5 to the -x equals 25. And again, I want to solve this. 5 to the -x equals 25. This one could have been in a previous, if I'm clever here and I use my properties, I get 5 to the -x. 25 is 5 squared. I can rewrite them both as the same base. I'm not going to have to take the natural log and do all that other fancy schmancy stuff, because I can rewrite them with the same base. If 5 to the this equals 5 to the that, then the exponents have to be equal to each other. In other words, -x has to equal 2, divide, x equals -2. And if I take 5 to the negative of -2, would be 5 to the positive 2, 5 squared is 25, so it does, check. All right, so what I'd like to do now, and I think we've got a lot of them, good ones here. Next I want to talk about, I want to do an example where we have to use the calculator to solve. And I've given you just one of these in the homework. Problem number 71, I think, is the only one that I gave you in the homework tonight. That's one where you have to use the calculator. But let's go ahead and take a look at one where we have to use the calculator to solve. And I'm going to do number 75, which is very similar. Solve. The natural log of x is equal to -x, and I want to solve that. Now, why do we have to use the calculator here? Well, if I rewrite this, natural log is log base e. E to the -x equals x, and I just can't get them out. I'm always going to have e's and natural logs there, and I'm not going to be able to do this one. This one would be very, very difficult to do algebraically. So I'm going to do it using the calculator. Here's how I'm going to do it. I'm going to go to my y equals, and in y1, I'm going to put in the natural log of x, and in y2, I'm going to put in -x. So y1 is natural log of x, and in y2, negative, remember to use the negative button down here, not the minus operation, -x, and I'm going to graph both of them. And I want to see graphically, where does the natural log of x equal x? We should kind of get an idea. Log base e of x, this is going to be an exponential growth. -x is going to look like that. We should kind of already have an idea what these things are going to look like. And then zoom standard, and I'm going to get the graph, and my graph is going to look like the natural log of x, exponential logarithmic growth, looks like this, and -x looks like that. And clearly, I can see that there is one point of intersection. These intersect in one. There's going to be one solution right there. Going to use the calculator to find it. So second, calculate, which is my trace button. Casio users, gsolve intersect. TI users, second trace, which is your calculate button. Intersect, go down to number 5. And I have to pick the two curves. Hit enter, hit enter. First curve, hit enter, second curve. So let's see. Oh, why is this giving me such a hard time? There it is. There we go. Gosh, Casio users are laughing at us. Theirs is so much quicker. gsolve intersect, boom, it just jumps right there for you, doesn't it? TIs, you have to hit the first curve, second curve, and do all that other fancy schmancy stuff. So I get that x equals, what is that there? 0.56714, yada, yada, yada. There's the solution. I don't need the y value. I'm solving for x. So that's how we can do it graphically. And really, any of these ones that we've done algebraically, all of them can be done graphically. You just graph the one side in y1 and the other side in y2, and then look for the points of intersection. The thing with doing it graphically is you only get decimal approximations. You're never going to get exact values. All right, that's it for 6.6. Lots of sample problems here. Now I want you to do homework 6.6. And homework 6.6 is on page 472. A lot of problems here. As I said, this is kind of a key lesson here before we get into the applications. The last 3 sections of this chapter are all of the applications, where we will be creating equations and solving them. So do lots of practice with solving them. And I want you to do, on page 472, I want you to do problems 5 through 27, odd, and then 33 through 41, odd, 45 through 49, a couple there that I want you to do odd, and then I want you to do 61, 63, 67, and then that last one, 67, where you have to do it on the calculator. Once you've got this assignment done, I want you to email the assignment to me. Email me the assignment, and I'll grade them and get it in. If you've got any questions, go ahead and ask. The answers are in the back of the book, but it doesn't show you the work. Very frustrating. It doesn't show you how they got the answers or the work for them, which can be really annoying. All right, ladies and gentlemen, good luck. And really spend some time on this assignment. Make sure you're really good. If you can solve all of these equations, the rest of the chapter, which is all applications and word problems, it will be a lot easier. The hardest part about word problems, and I'm going to start 6.7 with this, is actually coming up with the equation. Once you've got the equation, then it's very similar to the stuff we've seen here. All right, guys, good luck, and I'll talk to you again soon.